It really is called basic counting principles. And I think you'll see that this is related to some of the stuff we did earlier on sets. You saw stuff on sets earlier. Anyway, we're going to get into some Venn diagrams here. Here's the basic multiplication principle for counting. This would be for two tasks. And the way that I'm going to represent these problems is I'm going to represent them with two blanks. And it's the multiplication principle. So whatever you get here and whatever you get here, these are going to be whole numbers. And you're going to multiply them together. And here's how we're going to do this. If two operations, O1 and O2, are performed in order, O1 first, then O2, with N1 possible outcomes for the first one and N2 possible outcomes for the second one, then there are this times this. Just multiply these two numbers, possible combined outcome for the first operation followed by the second. So when you have just two things you're doing, this is the way it's going to work. And in many of our problems, you're going to have more than just two operations that occur. You might have three, or you might have four, or something like that. And they're all going to be in a context. And we're going to work through many. And so if there are three different possible outcomes, then I'm going to write it this way, or three different possible operations. If there are four operations, then I'm just going to write it this way. And you're going to multiply four numbers together. And that just gets generalized. So number two is kind of the general form of the multiplication principle for counting. All of your answers today are going to be whole numbers. And you're just going to be multiplying whole numbers. So let's take a look at how this works. You'll have a lot of different contexts. Okay, so the first one says how many two-letter code words can be formed from the first letters of the alphabet. Now this one is small enough that we could probably actually do it. All right, so you want a code word. Think about password or something like that. But the password has to be formed by the first three letters of the alphabet, A, B, and C. Those are the only three letters you can use. You can't use all the letters. And you want to form a code word, a two-letter code word out of this. So maybe we can just write these down. You could have A, B, and you could have a C, and you could have BA and BC. And notice it says no letter can be used more than once, and that's why I'm not writing A twice, or B twice, or C twice. And then you have CA or CB. So the only possible code words that we're talking about are those six. Now they don't ask you for those six, they ask you how many. We know by writing them down this way that there are six. But here's the multiplication principle up here. We have to select the first character, and then we have to select the second character. And we stop because we only need two characters. So the operations are select the first letter, and then the second operation is select the second letter. There are three letters to choose from here, but after we choose the first one, we can't use it again. That's what this says here. No letter can be used more than once. So when we make our second selection, we can't select out of three. There are only two letters left to choose from. And so to find the number of possible code words, we just take the three and multiply it by the two to get six. And here we listed them all, so you can see that that works. So this is what your problems are going to be like today. You're going to apply the multiplication principle. Hard part is just to figure out how many operations there are, how many times you're going to do something different, or even the same. All right, so I thought what we would do is just work through a bunch of these. There's this kind of problem in a lot of different contexts. And then there's some survey problems with sets that we'll go through as well. All right, the next one. In how many ways can three coins turn up? If you flip three coins, how many different ways can they turn up? Let's suppose that one's a penny and one's a nickel and one's a dime, so they're different. So what they're saying here is that these are different roles or different outcomes, even though they both have two heads. Even this one has both heads. They're different because they are ordered, and order is important here. For this outcome, the penny was a head, and the nickel was a tail, and the dime was a head. That's a different outcome than if the penny was a head and the nickel was a head and the dime was a tail. Okay. So how many ways can? All right. So for this one, we're going to flip the first coin, and then we're going to flip the second coin, and then we're going to flip the third coin. So there are three different operations if we have three coins. I suppose you could flip them all together if you like. But this assumes that we're going to be doing things in sequence. All right, so when you flip the first coin, the number of possible outcomes are 2. You can either get a head or a tail. Same thing with the second coin, same thing with the third coin. 2 times 2 times 2 is 8. So there are 8 possible outcomes when you flip 3 coins. And again, these are not too difficult to write down. You've got the outcome that consists of no tails. You've got 3 outcomes that consist of 1 tail. And all of these are different. You've got the 3 outcomes where you have 2 tails. That's listed right here. Head, tail, head, 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 tail, and tail, head, head. And then you've got one more outcome where, okay, 3 heads, 2 heads. I guess this one is that one. So this is 2 heads. So let me do 1 head. Head, tail, 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 head, tail, and tail, tail, head. So the 1 head. And then you've got the 1 outcome that has 0. So you can actually write these out because there's a small number. And if you count them up, 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes. All right. Now let me show you where we're headed with this. In chapter 8, we're going to do probability. And we're going to say, what is the probability of getting exactly 2 heads when flipping 3 coins? And there's going to be a probability formula that says the probability that event E occurs is the number of ways E can occur divided by the number of total outcomes in the sample space. So let me write that out. Number of ways. E is an event, and our event in this case is getting exactly 2 heads. For every one of these problems that we're doing today, in chapter 7, we can ask a similar probability question. So here's one in this context. And so probabilities will be numbers between 0 and 1. And so in this case, the number of ways that we can get exactly 2 heads, well, back here, we've actually counted them up. Here's one, and here's one. These 3 outcomes all have 2 heads and 1 tail. They're all different. So there are 3 outcomes where you get exactly 2 heads. None of these other 5 outcomes here have exactly 2 heads. And so the number of ways to get exactly 2 heads is 3, and the total number of possible outcomes is 8. And so we would say the probability is 3/8, less than a half. And you can either write the answer as in the fraction form, or you can write it in the decimal form. But today we're just counting. We're actually multiplying. All right, next one. All right, so you have a college freshman who has to take a bunch of introductory classes. And a college offers 2 intro courses in history and 3 introductory classes in science and 2 in mathematics and 2 in philosophy and 1 in English. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 total intro classes that this freshman can take the first semester. Okay, let's go to part A. You can see how in the same context, we can ask 2 completely different questions. If a freshman takes 1 course in each area, 1, 2, 3, 4, there are 5 different areas her first semester, how many course selections are possible? That is, how many course schedules that she would end up with. She has to have 5 courses. And so this is a nice application of the multiplication rule, but one of each of 5 different subjects has to be selected. So the way I'm going to represent that are 5 blanks where the numbers are multiplied together. So she has to select her history class, and then after she does that, she has to select her science class, and then after that, she has to select her math class and philosophy class and English class. Has to select them all. So the operation, the generic operation that they talk about above in our definition, the operation would be selecting a course from a specific discipline. And here are your 5 disciplines. Okay, so how many ways can she select the history class? Well, she can select the first one or the second one. There are 2. How many ways can she select the science class? Since there are 3 intro science classes, there are 3 different ways. Kind of get a sense of where this is going. Math classes, there are 2, philosophy classes 2, and English classes 1. Yeah, so you just multiply all those together and you get 24. There are 24 possible schedules that she could end up with. 2 times 3 times 2 times 2 times 1. Now, sometimes we model these with tree diagrams. So if it's hard to see in some other way, then think about a tree diagram where we have 2 history classes. I'll call it H1 and H2. And then after the history class is selected, then there are 3 science classes. Yeah. And then after the science class is selected, there are 2 different math classes. So math 1, math 2. And what you can do with the tree diagram, then you can plot out every possible path at the end. And you're going to have 24 different paths. This is going to be fairly tedious after a while. But what comes next is the philosophy, and there's 2 philosophy classes. So P1, P2, and then finally English after this. But when you're done, you're going to have, if you follow every path, you'll see that there are 24, I'm just going to say ... 24 different paths. And the different paths correspond to the different schedules. And you can see it more concretely in this way. All right, let's take a look at B. B is a slightly different. Here's another student. A part-time student can afford to take only 1 introductory course. How many selections are possible? So this full-time student here can select 5 different courses, and multiplication principle tells us how many different ways that can occur. The part-time student is going to only take 1 course. So we only have 1 blank there, but there's no restrictions on what kind of course it has to be, math, English, philosophy. So since there are a total of 10 possible introductory courses, that means that that part-time student can have 10 different possible schedules of 1 class. So it's really not a multiplication rule problem here. I think what you'll find is you got to read these very carefully. Changing sometimes of a single word can throw off the answer. Okay, why don't you try number 14, write your answer in the chat. All right, so let's start with part A, and then there's part B, and then there's part C. All right, so A is no letter repeated, and then B is the one if letters can be repeated, and then C is adjacent letters must be different. All right, just do part A. Do part A, and then we'll work on part B and part C together. So part A says how many 4-letter code words can be formed from the letters A, B, C, D, E, F, G if no letter is repeated. All right, it's a 4-letter code word. So you have to select the first letter, and then you have to select the second letter, and then you have to select the third letter, and then you have to select the 4th letter. So there are going to be 4 numbers that you're going to multiply together here. Now you're selecting from A, B, C, D, E, F, G. And if you count these, there are 1, 2, 3, 4, 5, 6, 7. 7 letters. All right. So in this case, there are 4 operations because you have to select each of the 4 letters of your code. In our previous example, it was a 2-letter code word. In this one, it's a 4-letter code word, and we have to select each of the 4 letters. Okay, so in the very first letter, we're not bound by any restrictions. So we can select any one of those 7 letters to represent our first letter of our code. But after that first letter is selected, if no letter can be repeated, then we can't use that first letter. Whatever it is that we selected, we can't use it. So when we go to select our second letter of our code word, there are only 6 possible letters to choose from. Well, when we get to the third blank here, we've already selected 2 letters. So we can't use the 2 letters that we've already used. So that reduces the number of letters that we can select for our third down to 5, only 5 to select from. And then finally, the last letter, again, we can't have any repeated letters. And so we've already used 1, 2, 3 letters in our first 3 letters of the code. We have to choose 1 more. We can't repeat these first 3. So that means that there are only 4 left to choose from. So There are 4 choices to do that. And for those of you that said 840, you are correct. When you multiply those 4 numbers together, you get 840. So you're going to find today in some of these problems, these numbers are going to get very large, particularly the next one. Let's take a look at the next one. Letters may be repeated this time. So we would allow a code word like BBBB or DDDC. Letters can be repeated, but a code word like KKKK is not allowed because K is not one of our letters. Okay, but we are still selecting our 4 code letters to make up our code word. The difference here is that when I select the first letter, there are 7 possible choices, just like the first one. But when I go to select the next one, I don't have to worry about repeated characters, repeated letters. So if my first letter was B, I could select B to be my second one. So every single time, since we don't have this requirement of no letter repeated, we have 7 letters to choose from. And that's 7 to the 4th power. So 2,401. Okay, the next one is a little trickier. This one just says adjacent. That means if 2 letters are written right next to each other, like if we have A, B, B, C, this one is not permitted because these 2 letters are written right next to one another. They're adjacent, and we're not going to allow that. But we would allow this. This one's okay. Repeated letters are okay. You just can't have any 2 letters that are the same right next to each other. All right. So again, there are 4 operations in the very generic sense of operation. The operation now is to select a letter. All right, so our first letter, we are unlimited in what we can choose. Since it's the first letter, it can't be adjacent to anything. So there are 7 possibilities. All right, let's assume that the first letter we chose was B. Now, since adjacent letters cannot be next to one another in our code, when we select the second letter, it cannot be a B. It can be anything else, but it can't be a B. So when we make the selection of our second letter, there are 6 different letters that we can choose. Now we know that this one is not B, so let's just assume that it's C. Now we move to our next one. How many possibilities do we have for the 3rd character of our code? Thanks. Joe, you are correct. We have 6. The only letter, see, we can match the B over here because B is not adjacent to this one, but we can't match the C. So there's only one letter that we are not permitted to use when we select the 3rd one, and that's the letter C. We can choose any of the other letters. There are 6 others. So 6 possibilities there. So we know that this can't be C, but it could be any of the others. So it could even be B. And then finally, in our last choice, well, again, the only letter that this one's going to be adjacent to is the B here. So once again, we have 6 different possible letters that we can choose here. So it's a little bit less than the 2401, but still a large number of possibilities. All right, let me go back to probability and let's use this context. What is the probability of selecting a 4-digit code word from the letters A, B, C, D, E, F, G, if no letter can be used? Now, the set of all possible code words, if there's no restrictions on them, all possible code words, that is, we're not putting a restriction on all the possible code words. That means that the first letter can be any one of those 7 letters. The second letter can be any one of those 7 letters. That is, we will allow repeats. We will allow adjacent characters to be the same when we're counting up all of the possible code words. So since we have 7 letters to choose from in each case, we're going to have the 2401. Now our event is, what is the probability of selecting a 4-digit code word from the letters A, B, C, D, E, F, G if no letter can be used twice? Well, number, if no letter used twice, and that one was the one where we took 7 times 6 times 5 times 4. That's this one right here. No letter used twice. So if we're going to calculate the probability of code word no letters used twice we would take the number of ways we can find a code word like that, and we're going to divide by the total number of possible code words if there are no restrictions on them. So we're kind of using two of the problems here and put them together in a fraction, and then you'd want to, reduce this fraction somehow. I think this is 343, and I think this is 120. All right, and then you could reduce it if you wanted. So I don't think you're going to see any probabilities in this section, but you will see problems just like this in the probability section coming up. So if this doesn't look all that clear, it probably shouldn't at this point. Let's take a look at number 36. 3 kinds of bread, 5 kinds of meat, and then 2 kinds of greens, and that's it. So 30 different possible sandwiches. So very good. Okay, let's look at 38. Using the English alphabet, how many 5-character case-sensitive passwords are possible if each character is a letter, uppercase or lowercase letter, or a number, a digit? Digits are from 0 to 9. All right, so what they're saying is that and it could be helpful for you just to write down a sample. It's a 5-character case-sensitive password. So it could look like this. A, lowercase c, D, 7, lowercase d. So that could be the password. Notice that it consists of capital letters, lowercase letters, but another one could be this, 01796. Could be all numbers, could be all uppercase letters, could be all lowercase letters, could be a mixture. All right, so as before, when we're doing these code numbers, okay, so Martial also has a very, very large number in there. Looks like it's close to 1 billion, both of them. Nope, kind of match. Brooke has one that matches. Okay, so we have 26 lowercase letters, 26 uppercase letters, and we have 10 digits. So when you add those together, you get 62. So the first character that you choose has to be one of those 62. So there's 62 possible characters that you could use for that first letter. Well, then we go to select the second letter. Now, there is no requirement on repeated characters. So one of the legal ones could be A75, right? That's legal because they put no restriction on whether you could use a digit over and over again. So the second digit, you also have 62 possibilities. Same for the third, oops, same for the fourth, and same for the fifth. So that's 62 to the 5th power. And so I think the 916 million number, it's close to 1 billion possible passwords. More characters you use, the more possible passwords. The less likely your password is going to be guessed. All right, let's take a look at number 40. Now 40 has 3 parts, so I'll break it down here. You have a combination lock, right? You're probably used to that at your high school where you had to, rotate the numbers. This one's a little different. It has 3 wheels, each labeled with the 10 digits from 0 to 9, and you had to rotate each of the 3 wheels to a specific number, and then if you match all 3 numbers, then the lock unlocks for you. It's a 3-digit combination, or maybe it's those ones that you just spin, like on a suitcase. So if you spin them and if it matches your number exactly. All right, so part A is here, and then part B is here. That's if the digits can be repeated. And then C would be the successive digits. So there's really 3 problems in here, 3 counting problems that you have to do. So you have to select the 3 different numbers. The first number can be 0 to 9. The second number can be 0 to 9. The third number can be 0 to 9. 10 times 10 times 10, and we say 1,000 combinations. And that's actually a misnomer. It really should be 10,000 permutations. But we call it combinations when we deal with locks for some reason. Okay, so part A is how many 3-digit combinations are possible? No digits repeat. Part B is if the digits can be repeated. And in part C, it said successive digits must be different. Now, saying successive digits must be different is similar to what we said before, that adjacent digits cannot be the same. So all three of these problems involve a three number combination lock. So you have to make three different choices in all three examples, because in every case, you're looking for a 3-digit combination number consisting of digits. For the first case, 707 is not permitted because the 7 is repeated. You can't have something like 556, but 137 would work. So you can't have any of these. So there's 1,000 possible combinations, but when no digits can be repeated, you start reducing the number of those 1,000. All right, so I see the answer in there, a couple of correct answers. The first digit, since the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if you count them, there are 10 digits. So your first character can be any of those 10. There's no danger, if you haven't selected a number yet, of matching some other number. But as soon as you select this number, let's say it's a 7, you can't match the 7 anymore. So there are only 9 characters, 9 digits remaining, and then 8. So those of you that said 720, that's correct. All right, what about the next one? What do you think? In this one, the digits can be repeated. Okay, good. That's the total number of possible outcomes. First character must be one of 10 digits, and if you're not worried about digits repeating, then the next digit can be 10 possible digits, and so will the last one. All right, and what about the last one where the successive, the adjacent numbers must be different? The first digit can be anything. If it's, say, like a 5, if we can't have successive digits the same, since the 5 was used here, it can't be used here, so that leaves 9 possibilities for the second. And let's say that the 7 was used here. Now this one over here could be a 5. It could match the first one. There's no restriction on multiple letters. It just can't match the 7. So there are 9 possibilities here as well. 810. Let's take a look at 54. There's 2 parts of it. Part A is right here. Ask the question, how many ways can these 2 positions be filled? And then part B is here, where it asks the second question. How many ways can the 2 positions be filled if the selection is made without regard to plant? All right, so earlier on we talked about 2 operations. And so if you break this one down, you have 6 officers from A, and you have 8 officers from B, and so total you have 14 officers. Now, in the first problem, it says how many ways. All right, so I see some answers in there, 48 and 196. 48, looks like that's the common one. Okay, so in the first operation we're going to do is we're going to fill position V. We're going to fill that first vice president position with an officer from A, and there are 6 different officers from A, and we can choose any one of those 6. So there's 6 ways to choose the first vice president, since we're selecting that vice president from plant A. Our next operation is to fill the second vice president position with somebody with an officer from plant B, and there are 8 officers from plant B. So there are 8 possible choices, 48. So of the answers listed there, 48, you're correct. All right, so part B. Part B says, in how many ways can the 2 positions be filled if the selection is made without regard to plant? So we're not considering the 6 officers. It could very well be that both of those vice presidents are people that we select from A, from plant A. But what we're going to do is we're just going to pool all of those officers together and think that we have 14 officers to choose from. Now we want to assign the V1, and after we assign the V1, we want to assign the V2. Now there's 2 people that we want to put in these leadership positions, right? And one person cannot take 2 vice president positions. We want the first vice president, we want the second vice president. Okay, so let's appoint the first vice president here. Since there are 14 to choose from, if we're not going to worry about where they're working currently, then there are 14 ways that we can choose that first person. And then after we choose that person, That first person we selected is no longer in the running for the second vice president position. So that leaves only 13 remaining. And I think the 182 number is the one that works there. So you're going to have a lot of problems, and you can see there's one result, and it's the multiplication principle. It depends on how many things that you have to do, how many choices you have to make, how many decisions you have to make, how many, they say, operations you have to do. So first figure that out, and then just count the number of ways, and then apply the multiplication principle if you have to do multiple tasks. Select one vice president, then select another. All right, the other thing that you're going to see here is, in these, I'm not sure, these are part of survey problems. So you may have seen some survey problems before in courses that you've been in. And the survey problems are all based on the following result from a Venn diagram or from sets, however you want to think about it. You have a set A and a set B. And if you're interested to know about the number in A union B, sometimes we refer to that as A or B. And here's the region we're talking about. How many are in here? If you join those two groups together, A union B, this region right here in the middle is in the intersection between A and B. So A intersection B is right in the middle. And here's a formula for calculating the number in A or B, which is all of this inside the circles. I'm going to draw another Venn diagram here. All right, here's how you do it. The number in A or B, which is this region up here, the red and the purple shaded region, everything inside both circles. What you can do is you can add the number in A, I'll indicate that in red, and then you can add to that the number in B. So it's all of these. Now, if you added the red region and the purple region, you can see that the middle region is doubly shaded. That means that I've added that middle region twice. And if I'm going to just count up the number up here in these three regions, I don't want to add the middle region twice. So what I'm going to do is I'm going to subtract out the number in the intersection. And this is called the general addition rule. So the next kind of counting we're going to do is going to be based on this here, this result. And they call it the addition principle. And so there you see it. All right, so let's take a look at what they're after here. They give you the Venn diagram. And not only do they describe the intersection, A intersects C here, they give you the complement information as well. This is A intersect B complement. Oh, maybe I should draw B complement for you. The big rectangle is called U, the universal set typically. And then A complement would be everything that's not in A, everything in the universal set that's not in A. So we don't want to shade anything on A, but you want to shade everything else, including the piece of B that's not in A, and including the rest of the stuff that's not in either A or B, but in the universal set. So that would be A complement. All right, let's take a look at one of these, and maybe we'll start with number 18. They give you some information here, and then it says there are 4 different regions here. This region, this region, this region, and this region. So when you're done, you're going to have a Venn diagram that looks like this, but you're going to have numbers in each of these regions. All right, so maybe I'll just do problem 18 right here. All right, so here's how these work. I'm going to start with the intersection, because this really is one of the regions that they've given us. It's in our diagram here. A intersect B is right in the middle, and they're saying that the number of items in the middle is 20. So I'm going to put 20 in there. They also tell us that the number in the universal set is 100. So when we add those 4 numbers that we're going to place in this diagram, they have to add up to 100. The number 100 itself might not appear in the diagram anywhere. All right, let's go over here to A. The number in A is 40. Now remember, A is this whole circle here. And we know that 20 is in this piece of it. So if in all of A, there are 40, here, then how many must be in this little region over here? 20 also. If 20 is in the middle and 20 is in this region, 20 and 20 is 40. That would match this criteria over here. Let's move on to the number in B. The number in B is 60. Well, B consists of these 20 plus everything that would fall in this region here. So if B is 60, the number that goes in there must be 60 minus 20 because 20 is already there. So we must put 40. And then finally, the number in the union between A and B is 20 and 20 and 40. That's 80. And then they tell us in the universal set, there are 100. So how many must be outside all the circles? Those add up to 80. So 80 and 20 be 100. So this is what the Venn diagram would look like with these clues here. So I'm not sure what they're going to ask about, but if we do A, the number in A intersect B complement, that's the 20. The number in A intersect B is equal to 20. The number in A complement intersect B is equal to 40. And the number in A complement intersect B complement, which is the outside region, would also be 20. So I'm not sure how they're going to represent this in the exercises, but it says determine the number of elements in each of the 4 regions. So you can either do it this way or you can write them out. Okay, why don't you try number 20? And so you can just give me the numbers as you read from left to right. So you're going to give me 4 numbers, and those 4 numbers should add up to 200 this time. So do number 20. Okay, so we have the number in A is 65, but we don't know how many of those 65 are in this region and how many of the 65 are in this region. We know B has 150, but again, we don't know how many are in each region. We know that the union is 175, so when we add these 3 numbers together, we should get 175. So the first thing we're going to do is we're going to try to figure out what's in the intersection there. And we know that the number in A union B is equal to the number in A plus the number in B minus the number in the intersection. And because they gave us 3 of the 4 numbers in this equation, we can plug in the 3 and then find the missing 4th. So for example, in number 20, they give us the number in the union is 175. So this number here is 175. They tell us that the number in A is 65. They tell us that the number in B is 150. And then we can deduce from what they've given us what this number must be. So 65 plus 150 is 215. So what do you have to subtract to get 175? Okay, good. Must be 40. Must be 40. This is 215. 215 minus 40 is going to give us. Okay, now with that, since that is the number of in A intersect B is equal to 40, then we can put the 40 there and then work backwards from there. So for example, the number in A is 65 and we already have 40 there. So that must mean that this is 25. The number in B in this problem is 150 and we already have 40 there. So 150 minus 40 tells us that 110 then would be left over. So all in B, this whole big circle is 150. A, the big circle A, you'd add those 2 numbers and get 65. The number in the intersection based on this formula is 40. And then the last thing they tell you is that the number in the universal set is equal to 200. We already have 25, 40, and 110. We already have 175 accounted for. So if you take 200 and subtract 175, you get 25. So that must mean that 25 are out here. The idea is to put a number in each one of these 4 regions. So the 4 numbers are 25, 40, 110, and 25. Okay, let's merge over to an application. Well, let's see. There's another kind of problem before we get there. You're also going to see this Venn diagram information in a table like this. So maybe this table would be a little easier to figure out for you. Let me do one and then ask you to do one. Okay, so the number that we're looking for right there, since it's the intersection between the A and the B, that number right there would be the number in A intersect B. The number right here would be the number in B intersect A complement, right there. So that's where A complement and B intersect. This one here would be the number in, okay, so it's A with B complement, A and B complement. So it's the same four regions that are going to appear right in here. And so they want them to be in a table as opposed to in a Venn diagram, but we'll do both of them. Okay, so here's where you would put the number in A. If the number in A is 55, well, here's A. A consists of these two numbers. So when you add these two together, you should get 55 because the number in A is 55. These are the totals. The number in B is 65. Well, B consists of those two regions, one that intersects with A and one that intersects with A complement. The total for B would be 65. The number in the intersection between A and B is 35. Well, that's this number right here, 35. And the number in the universal set is 100, and that will always go in that spot. Number in the universal set. Now, these numbers aren't difficult to work with. Just keep in mind that these are row totals. So 35 plus what is 65? 35 plus what is 55? And then once you get these two numbers, you can figure out what these other numbers are. In fact, you could figure out what this one is and what this one is, just by kind of working backwards, using some subtraction. So for example, 65 plus 35 is equal to 100. 55 plus 45 is equal to 100. 35 plus 20 is equal to 55. And then 20 plus 15 is equal to 35. And then 35 plus 30 is equal to 65. So we were given these numbers in black here from our 4 clues, and with those, we could fill out the rest of the table. Now let me show you where this appears on a Venn diagram. Well, you know. So if you're having difficulty with the Venn diagrams, you might want to go to this table approach, because A intersect B is right in the middle. B intersect A complement is this region, 30. This region here is inside A but outside B, so A with B complement. And this region out here is not in A and not in B, so it's the intersection between A complement and B complement. And if you add those 4 numbers, you're going to get your 100. And what you should notice about this problem is that these 4 numbers are the same 4 numbers that appear over in the Venn diagram. So it might be easier for you to complete this table than to complete the Venn diagram. But the two are equivalent. They give you some clues and they ask you to find the missing pieces. Okay, let's do one more problem. And this is an application, market research. Okay, it's basically the same problem, but it gives you a context this time. And so you have a survey of 800 small businesses. It indicates that 250 own a video conferencing system, 420 own projection equipment, and 180 own both the video conferencing system and the projection equipment. So I'm going to do a Venn diagram here. Instead of just labeling my circles, my sets as A and B, I'm going to put a title onto them. So this one here says the number in the universal set is equal to 100. That's the total involved in the survey. They told you that up front. So the 4 numbers that we're adding in this Venn diagram here should add up to 800. That's how many were involved in the survey. The first circle deals with those that own video conferencing system, Zoom or something like that, video conferencing system. Now I can't place 250 in here because I don't know how many of the 250 go in this region and how many of the 250 go in this region. So I'll just continue on. 420 own projection equipment. All right, so over here we have projection equipment instead of set B. These folks in the middle here would own both video conferencing program or system and a projection equipment. They own both. The folks that we would put out here outside the circles, those are the businesses that own neither of those two, neither the video conferencing system nor the projection equipment. Okay, we have 1, 2, 3, 4 numbers to place in here. So it's a problem similar to the earlier one. You just have to use the words. Where are you going to put this one? The keyword and. And means intersection. So 180 own both of those things. See where that would go? These folks in here own both. So we have 180 in there. That's where we place the first clue. Now from here on out, we do subtractions. We know that 250 own the video conferencing system. So that means these 180 plus some more add up to 250. So what must go in this region here? Okay. So then you can see that there are 250 businesses that own the video conferencing system. You add those two numbers together. All right, and then 420 own the projection equipment. So 420 would be what we get in this whole circle, but we already have 180. So I think that's 240. And then if you add 70 plus 180 plus 240, you get 490. So that must mean then, since we had 800 in the survey, that 800 minus 490, which is 410, that must be the number outside all of the circles because they must not own any of it. So the idea of the applications is to create the Venn diagram first and then go answer the questions that they give you here. So we're counting the number in each of these regions. How many businesses in the survey own either one or the other or both, video conferencing system or projection equipment? So that would be, you'd have to add the 70 plus the 180. So it's really doing the or there. So that's the union. And then add the 240. All right, so we did that down here, 490. How many own neither? Well, we calculated that there to be the 410. How many own projection equipment? So we're talking about these 420, but do not own the video conferencing system. So of these 420, these 80 also own the video conferencing system. So these 240 are the ones that own the projection equipment, but not the video conferencing system. So these are called survey problems. And the idea is we're going to use the addition principle for sets to count up the number in each of the regions.